Hello again, Calc 3 Scholar, welcome back. And recall last time we discussed finding this integral, the double integral of x, y, dA over this disk region. We first looked at it in rectangular coordinates and found out that those limits were pretty complicated. That was going to give us a difficult integral, so we went ahead and converted that over into polar, and found that when we did that, the integrand got a little more complicated, but our limits simplified quite a bit. And it turns out this is a bit easier to solve. So let's go ahead and finish this problem out by evaluating this integral, and then finally we'll take a look at it in Calcplot 3D just to make sure everything lines up. So let's get started. So first thing, this was our integral we ended up with, so let's just go ahead and write that in a little cleaner form up here. And this is what we got. So we got the integral of r cubed cosine theta sine theta dr d theta, integrating from 0 to 3 in r and integrating from 0 to 2 pi in theta. So you notice that our first differential here is dr, so we're going to integrate with respect to r first, so our cosine theta sine theta terms are just going to be like constants for this first integral, and we're just going to have to focus on this r cubed, which is pretty simple to integrate, right? That's just going to be r to the 4th over 4. So doing that, we get r to the 4th over 4. We want to evaluate at our limits 3 and 0, and of course if we plug in 0 for r, that's going to be 0, so we're really just concerned about plugging in this 3 for r down here, and if we do that, 3 to the 4th, turns out that's going to be 81 over 4. So we can just take that 81 over 4 constant and bring that out to the front here, and now we have this integral to work with, which is a little bit more difficult because we got two trig functions. So what we want to do here is find a u, and we could actually make u cosine theta or sine theta, it doesn't really matter, but if we make u sine theta, that works out a little bit better because the derivative of sine theta is cosine theta, so it'll cancel out perfectly. There won't be a negative sign in here to worry about. So let's just go ahead and use u substitution with u equals sine of theta. So if u equals sine of theta, next thing we got to do for u sub is, if you recall, is take the derivative of u with respect to theta. So pretty simple, du d theta is just cosine theta. And now we want to solve for d theta, which is just going to be our du divided by cosine theta. So now we got really all that we need for u substitution. So what we can do is go ahead and take our u here, and we're going to plug that in for our sine theta term. And then instead of this d theta term, we're going to go ahead and replace that with du over cosine theta. So let's go ahead and plug those in. And one last thing that's really easy to forget is since we're changing this d theta to du, integrating with respect to u, we got to change our limits to be with respect to u. So let's go u of 2 pi and u of 0 here. Alright, so plug in all those in, we get 81 to the 4th out front, our integral of cosine theta u times du over cosine theta. And of course these cosine thetas cancel out pretty conveniently, and we're just left with u du. It was a pretty simple integral. And if we wanted to find our u of 2 pi, well, all we got to do is apply this function up here. So u of 2 pi, that's just going to equal sine of 2 pi. And u of 0 is just sine of 0. So plugging those limits in, we get 81 over 4 constant times the integral from sine of 0 to sine of 2 pi of u du. Now, this is pretty straightforward from here. We take the integral of u du, that's just going to be, well, I guess let's keep this 81 over 4 out front. And we got u squared over 2. And we're going to evaluate that between sine of 2 pi, which is 0, and sine of 0, which is 0. So as you can see, this is just going to equal 0, because you plug 0 in for u, it's both sides, this is going to be 0. Which may be a little suspicious. Like, does this really cancel out? Seems like kind of, maybe, I'm not really sure. But to check this, it's going to help to plot this out in Calcplot 3D. So let's go ahead and plot this out to make sure that we're not doing anything crazy here. Alright, so opening up a web browser here, let's just go Calcplot 3D here. And first thing that pops up here, Calcplot 3D. We don't really care about this function here, so let's get rid of that. We're going to go ahead and add a region. and we already converted this to polar, so let's go ahead and convert this and do polar. We know that we went from r equals 0 to 3 to look at a region, and we went from theta equals 0 to 2 pi, so that's convenient they got the pi in here, so let's just put that 2 in. And you can see it gave us that region that we were looking at, that we plotted out earlier here. So we're on the right track here with our region. And now we just got to change our function. Our function here, you can see Calculate3D likes it in terms of x and y still, which is actually easier for us. So let's just do x times y. And this is our surface here we're trying to find the volume under. And let's just zoom out a little bit to get a better look. And you can see it looks like we've got what would be a volume here on the top that would yield a positive value, whereas this would be a negative sign volume on the bottom. And it looks like these are about equivalent, right? So these are going to cancel out. It does make sense that this double integral is 0. So let's go back to a slide here, and let's go ahead and box in our answer here. So in summary, we looked at how to find this integral, change it to polar coordinates. We evaluated it, and wasn't too bad. Had to use some u sub, and we ended up with 0. Checked it in Calculate3D, everything lined up. So there it is, finding double integrals in polar coordinates. Hope this helps, and until next time, take care.